Our next speaker is Carl Brauhart. He'll be talking about a geologist's guide to using assay labs. So just a bit of background on Carl while we're getting set up. Carl is an exploration geologist with over 30 years of experience in gold and base metal exploration, spending much of that time working in frontier areas of WA on grassroots projects. He is interested in geochemistry, both exploration geochemistry and ore deposit geochemistry, and has a passion for fieldwork, particularly mapping. Carl has maintained a close association with the Centre for Exploration Targeting at UWA, where he is the lead researcher on project ore deposit geochemistry research effort. Please welcome Carl.
Sorry, I forgot that I'm old. I think in here I'm a young man that doesn't need glasses, but that's not true. Hands up the geochemists in the audience. Are there any geochemists here? Good. Oh, one. Sorry, you were hiding behind the pole, which is where you should be. How many people think of geochemist? I hope most of you don't know me, but those who do know me, do you think of geochemist? Good, that's good as well. You know, I'm a mapping geologist. And the point that I want to get across is that our training is geology, and some of us fall into geochemistry. But my passion is mapping. And yesterday I decided I was going to wear my field outfit, but my wife took me aside and said, "This is not primary school where you go in and tell the kids about geology." And I lost that argument. But what I realised is it took me, with my supposed interest, and some people mistakenly regard as expertise in geochemistry, took 20, 25 years to become comfortable with the options in assay labs, the commercial laboratories available to us. So I wrote it up. It's in draft form with the AIG, but I've provided that draft to Donna for general distribution to you guys. If it ever comes out, published by the AIG, and it costs $10, well, you can give $10 to the AIG if you like. But the main point I wanted to do is to disseminate that knowledge, because there's a table in there we're going to have a look at. Somebody in year 6 could remember it by rote in half an hour. We're a bit more stupid than that. It would take us a few days, but you could have it on your computer, and then you're the expert on what the options are available to you in the lab. What I'm trying to say is it's not that hard. All right, this is the preface to that draft document. I hope it becomes a little handbook in the AIG. There are 3 fundamental questions we can answer with geochemistry before or after we go to the field or the core shed. And it's an iterative loop. Finding out more about the rock type so we can constrain the stratigraphy. Don't need to write anything down unless you love taking notes, because the presentation is also going to be publicly available. The hydrothermal alteration and the mineralisation. So they are the practical problems that we face as exploration geologists every day, where geochemistry can assist us. It is not the end in itself. Yeah, we think of, we know that we're going to integrate our data, but then half the time we forget. And you get people sitting in offices who are just geochemists. You guys need to be the geochemist. When we use that label, it's any exploration geologist who knows a little bit about geochemistry and uses it to do their job. And you should all be doing that. And that was my list of references, and that's where this comes from. It's all the people in the industry who've told me something that I've remembered. I might have butchered half of it, so I'm not going to hold any of them responsible for what I'm saying. But the thing is, as you go through and you gather experience through your career, you'll build a list like this in your area of so-called expertise. There's a table. You could learn that. We're going to go through these methods one by one. There is a method that is the best for different applications within exploration. And they're the main ones. Then there's a second table of things that you might use, but you might go through a whole career and not see these. The ones that we use again and again were on table one. The handbook is not really about sampling. The next talk is about sampling, I believe. Yeah, Donna's nodding. Yeah, I've just got a few thoughts on sampling. All the finest geochemistry in the world is not going to save a poorly taken sample. It is a fundamental thing. It's like ground selection. All the finest technical work in the world is not going to save poorly selected ground because there's nothing there to find. Soil samples, mostly where we work in an arid environment, that doesn't really matter too much. It's just ground up rock. It's probably the equivalent of sea horizon, unless, of course, it's saprolite and or transported over burden where the soil horizon, again, is not that relevant because everything going on is much deeper. I think, we used to do BLEG, take the largest sample we could for stream sediment sampling or even soil sampling. I think we've realised now in the industry, the finer the better, and that has reached its ultimate destination, I think, with that ultra-fine fraction. Having purely clay takes away the nugget effect altogether, and we'll get to that. If you're in an arid environment, be especially careful about wind blow and sand. That can comprise 99% or more of a poorly taken sample. Again, we're going for fine material. Yeah, it's very difficult to get a uniform sample type as we go across different regolith types. So we need a map. Commonly that's done by satellite. I think it's so much better if you get a geologist out in the field. They might trip over a gossan, but the main thing that they're going to do is come to terms in their own mind with what really is erosional, residual and transported regolith. And we tag those accordingly and we interpret those domains differently. Yeah, it's important to do orientation surveys if we have comparable mineralisation to what we're trying to find, but be very wary of the drill dust and so on, contamination, and I think that's for diggings, they can disturb things, but you can normally dig underneath that, just dig a slightly deeper hole to get through that potential contamination. And we will be looking for multiple things. We're looking at different size fractions, depths, and assay method. And remember that you're looking for the best signal to noise ratio, not the highest raw values. It's how obviously different are anomalies to their background. Oh no, not another one. Well, that's right. You may just be doing an orientation for one element. I'd say, no, don't do that. We want to have the multi-element signature. So we try and, or we don't try, we do, we make a multi-element index and we're interested in the greatest contrast for that, not any one individual element. It's not just about the commodity you're looking for. When you assess a new prospect, take some rock chips, you get some ore grade samples. They're not representative and they're not meant to be. We want to take the most biased sample possible to get the smell of that particular body of mineralisation. But then you don't plan a drill program on the basis that that's representative. I've seen so many things drilled that any competent geologist could have written off in half an hour looking at the outcrop. When we're drilling, contamination's a big issue, but I think that's going to get covered in the next talk. Oh, no, not another one. Oh, right. This is a big one with me. When you're doing air core and you get to that last gasp of a sample, it's on the top of the bucket. What happens to it? It's tipped on the ground. It's on the bottom and you never see it again. That last gasp is the most valuable sample. It's the least weathered. It's the closest you're going to get to a fresh sample. Get the drillers to take an ice cream container size in a second bucket, put it aside, flatten the pile and put it on top. Then when you sieve it, again, we're not after a representative sample. We've done that all the way down the hole. But for this, we want the least altered chips and you pick them out of the sieve individually. And you're better off with a small fresh sample than a big sample with weathered chips in it. Some holes, it doesn't appear that it matters so much. It's much the same at the bottom, at the very, very bottom as it is in the rest of the meter. Others, it is completely different. So don't take a spear sample. Yeah, that's not for me. That's for the next talk. Right. Should you use OES, AAS, or ICP-MS? These are different measuring instruments in the lab. They may cost a little bit more for ICP-MS, but you use ICP-MS every single time. Even if you think, oh, I only need OES to tell me if I've got mineralisation or not, that data will be returned to for other purposes, and you will regret the commonly 500 times higher detection limit by AAS, OES. Don't do it. The money is always best spent. At a lot of labs, it's, $5 per sample, more or less, the difference. Yeah, lost opportunity. Here's an example courtesy of Scott Halley. It's in a porphyry copper district where the area was soil sampled and done by OES. And this is one of those rare occasions when they went back and they resampled the same pulps by MS. And does it do? Oh, shit, not that one. I don't get a light. These three clusters of red stand out as anomalies, so you can see how much better the ICP-MS is. But not only that, the two on the left are blind. There's not the alteration and mineralisation at surface that you have in the one in the southeast corner. And you can only see that at all clearly with the ICP-MS data. And if you look at the probability plot, and I better explain that for those who don't know how a probability plot works, it's a whole lot better than a histogram, but it shows, again, the distribution of values in our population. So 0 is the median value, the 50th percentile. -1 is -1 standard deviation, -2 standard deviations, etc. So what you're looking at there is the background lithological population up to about 1 ppm, and then we transition into mineralisation. Problem with the OES data, which is the top, is that we're well into mineralisation before it even registers. It's telling us two completely different stories, isn't it? And that's the value of the ICP-MS. The published or advertised detection limits are not set in stone. When they're reading the element on the instrument, if they read for longer, they will get lower detection limits. They can take more time to clear the instrument. It's called instrumental contamination. Now, it's not them being dirty, it's just that it takes time for a clean solution to remove, and elements like tellurium are particularly sticky. So you get higher detection limits than you'd like for tellurium, but you can get lower ones if you ask. That's some of the labs, others not. Okay, so now we're going to move on to the different techniques, what they're ideal for and what they shouldn't be used for, and the element suites that they're appropriate for. So you've got to remember those things. It's, they're useful for certain elements and absolutely ideal for those elements for certain purposes, not for others. So there we are. I've pulled out one row of the table and we're going to keep doing that. We've cut it up with scissors into strips. Tells you the digest, the type of acid, and those elements that it is useful for. Aqua regia dissolves sulfide, so it works on fresh rock. But typically we use it for surface sampling where we've got the weathered product where it's dissolving the iron oxides and all the materials that the sulfides have weathered to. The great thing about aqua regia is that we get gold and most of the pathfinder elements for any mineralisation style you're going to be looking for, except things like LCT pegmatites, where so many of the minerals are refractory. But for most, for hydrothermal systems with sulfides, it's very useful. So we pay, if we want to have a fire assay on top of 4 acid, or where we're using more than one method, we're going to be paying at least $10 extra. So you've got to think, if the aqua regia is not a complete digest, all the rest of it, I really should use 4 acid. Unless you're wanting to map the lithology with your soil sampling, our aim is to take as many samples as we can that are effective, fit for purpose with our exploration budget. And aqua regia is unrivaled for a lot of soil and rock, surface rock sampling campaigns where we're at the regional scale and we're trying to find anomalies in the first place. We can wait to define alteration and the detailed stratigraphic setting when we get down to the prospect scale. We will be supplementing that data with lithogeochemical samples regionally around our map. But when we're wanting to take 3,000 soil samples, we don't necessarily need to go to a more expensive technique. We really want to add those few major elements. I can't stand it when I don't have iron and manganese. They are so important to level the data because so many of our elements that we are interested in get scavenged. Mark Arundel has a beautiful presentation where there's 1,000 ppm copper drilled. And this is not to do with mineralisation at all. It's at the top end of what iron scavenging can do. So do not, in the surface environment in particular, ever drill raw single element anomalies. You could get really disappointed. Mercury, the forgotten element, because it can only be done by mercury at good labs that take care not to boil off or steam off those volatile elements. And it is the digest done for ultrafine. Yeah, I really reckon it's underused. People insist on fire assay. I've got to have fire assay. That's bullshit. You don't need fire assay until you're drilling out a resource, in my opinion. Aqua regia is perfectly reliable. It just underreports slightly. But in exploration, we couldn't care less if it's 0.91 or 1.1 grams per tonne gold. It's a screaming anomaly. What I want to know is what elements are going with that highly anomalous gold. It's about fit for purpose and getting the maximum bang for our buck out of our exploration budget. There are labs that insist on giving you the full 48 or even 63 elements by aqua regia. Those elements there, like aluminium, potassium, and then your really immobile elements, which are in refractory minerals, aqua regia doesn't dissolve them. Those data are worse than useless because somebody sometime might use them. Dale, is it possible to take a pair of scissors and cut those elements out of the database and never load them? So aqua regia is not for lithogeochemistry. About the best you could do is domain mafic from Felsic based on the chrome values, where the chrome is not in a resistate phase, it's in the mafic silicates. I'm going to emphasise, spend more at a tier 1 laboratory. I shouldn't really, well, no, you work them out yourselves. It won't take long. I don't need to advertise anybody in particular. Cheap labs can lose not just mercury, but antimony, arsenic, thallium, selenium. They're volatile and they can steam off. And we run into reprecipitation issues, where when we get 1,000 ppm silver or antimony, really high lead, we need to turn to a different method to get an accurate result. So these are the elements that it's ideal for in pink, and then the control elements that we really want to have in green. So notice that it's not covering lithogeochemistry or alteration, which we'll get to later. And I've put here iron and manganese are shaded, and the typical elements that they scavenge, but I'm emphasise typical. All of those elements on there can be scavenged by iron or manganese or both together. All I'm saying is plot iron and plot manganese versus these elements every time. So there's an example. We've got quite strong iron pathfinder element correlations, but we can see our mineralised populations standing up above that. So what's an anomaly is not a constant thing. It's relative to that main correlation in the background data. Manganese is doing it too, and it's doing it for subtly different elements in some cases. Okay, so let's move on to 4-acid. 4 different acids, including hydrofluoric, which is a safety concern. A lot more elements are useful, such that it is the go-to where we're wanting to cover mineralisation, alteration, and lithogeochemistry. I won't go into geometallurgy other than to say that 4-acid on all of your thousands or tens of thousands of samples in a drill out can save or earn hundreds of millions of dollars. So if you're saving money by doing every 4th sample by ICP-MS and OES for the rest, or not using 4-acid consistently, or changing up your element suites, that decision will really bite you, especially if you don't even do a good geometallurgical program, which most mines up to now haven't done. But if you do, 4-acid is the way to go. It's not quite a complete digest, so that can bring us trouble. If you're mining, if you're exploring tin, drilling out something with cassiterite in it, you've got to go to fusion and other commodities beside. You must use fusion for LCT pegmatite. So it's not a cover-all, but we can still get very, very useful lithogeochemical data from 4-acid in a lot of cases. Yeah, so that's one of the disadvantages, is that it's not quite perfect. So the complete digests are fusion and now recently laser ablation ICP-MS. So we're talking about things like zircon, monazite, xenotime. So obviously if you're doing rare earths, you want to go fusion. Tourmaline and so on, you can read those. And we don't get silica, because that goes up the fume hood. That hydrofluoric acid breaks down all the silicates, but in liberating those elements into solution, we lose the silica. We can't do gold. We need another method. And if gold is not part of your economic suite of metals, I would do aqua regia. Again, we've got trouble with boiling off volatiles, and at high concentrations, we have the reprecipitation issues. Wet chemistry. With wet chemistry, you're always going to have those two issues. But there, look at that beautiful broad range of elements that 4-acid is generally fit for purpose. I've shaded the elements where you can or you will have problems. And the mineralisation elements that it covers, it's broad, but it's not gold, palladium, platinum, or mercury. Our alteration elements, mostly the major elements, and our lithogeochemical elements. So it really is a very good method covering a lot of things. This is becoming a thing of the past. It depends on which lab you go to for the detection limits by 4-acid and fusion. The Holy Grail was, can we get 4-acid type detection limits, but a complete digest by fusion? And that's being achieved now. But back in the old days, I've even got the right slide. No, I don't think I have it. That's the next slide. There we are. I meant to go back and forth. So that's the difference between 4-acid, which is high precision, but not quite right on the accuracy because it's not completely digesting things like zirconium, versus the accurate data. It's digesting all of it, but it doesn't have the same precision. Which would you rather use to discriminate the different populations? Well, I think things are clearer by 4-acid. And the reason it's working is that the underreporting is largely proportional, but there are other examples where that's not the case. So if you're using your 4-acid data project-wide, do some fusion checks and plot them against each other for the same element, same sample, and see how well they compare. Up the high end of the aluminium, you can see we're starting to get some reprecipitation. The black and white graph shows how bad that can be at a poor lab. So again, do some fusion checks. Showing the same for titanium. And sorry, these are all, you can see in the title from Scott Halley. And here we're seeing that antimony is not completely digested by aqua regia, and that's quite common, and I've learned from Scott. I don't mind. It's still proportional enough, and in exploration, the absolute value, we're still going to get those multi-element relationships using aqua regia, but we need to remember that it may not be complete. As we move from exploration, where the precision matters, towards the mine, where accuracy matters. The difference between 90% leaching of gold with aqua regia and 100% by fire assay, well, of course, that matters if you're calculating a gold resource. But out in exploration, it's fine. Fusion is total. We make a glass disc, and then that gets dissolved in acid. So the silicates have been broken down to a glass which has no crystal structure. Now everything's going to dissolve. We don't even need HF to do it. So it gives the same comprehensive element suite, almost, and it's an absolute must for things like lithium, tantalum, tin, tungsten, or chromite. If we're doing LCT pegmatite or exploration, obviously we can't use a lithium borate flux because that's going to invalidate our lithium analyses. So you're either going to have to lose lithium and boron or lose sodium. And sodium is one of the important alteration elements. I've mentioned that we are now getting to fusion with those nice low detection limits. And we get silica. So I've mentioned we're going to lose one or other of lithium, boron, or sodium. Fusion is still a wet chemistry method. It shouldn't have the problems of reprecipitation that we otherwise have. Except for barium. I haven't mentioned that barium can't be done by any of these reliably if you've got barite in the system. It just reprecipitates. And again, we don't get gold. So we've still got to be, actually, I'm not so sure about the loss of volatiles. I'm not sure how that's controlled in the glass disc. I may have just copied that from 4-acid. I don't think that is the problem that I'm saying it is there. No, neither should we have the reprecipitation. I think we'll just delete that. So there's our element suite, which is fantastic, but like I said, we're either going to lose lithium and boron at the top or sodium. XRF. This is the go-to for major elements. It is accurate, but it doesn't have the precision. The detection limits are not nearly as low as we would like, except for the major elements where XRF is the gold standard. And it's extremely widely used in iron ore exploration. Gives us loss on ignition. The trouble is with the detection limits, we may be able to use it for some of the transition elements and so on, but it's not all that useful for other applications. Okay, so just quickly on the laser ablation ICP-MS, it's a complete digest. If you couple it with XRF, I use it a lot. I love it. It's not a wet chemistry method, so you don't need to worry about reprecipitations of boiling off or any of that. But it's not yet widely available. The fused disc, again, means we're going to lose one element or others. And although most of the elements have beautiful four acid-like detection limits, there are a couple which are not so great, tellurium and selenium. And again, we're not going to get gold. Oh, right. So there's our suite of elements. Fire assay, well, it's gold, platinum, palladium. It's the gold standard for those elements, but obviously we've got a very limited element suite, but people are working hard on doing other elements reliably by fire assay. This was the OSNACA project. For those who don't know it, there's about 800 or 1,000 ore samples assayed for gold by Aqua Regia and by fire assay. And I was chirping around the CSA global office a few years ago, you're wasting your money doing fire assay. Look at this beautiful correlation between the two, you know, from background levels up to bonanza grades. And one of the resource geologists said, do a QQ plot, and I bet you there's a 10% undercall between 0.1 and 10 grams per tonne. I said, QQ what? That's where we have samples. We're looking at the data, but we break apart looking at sample. There's the two values from the same sample. We just put the data in order from lowest to highest for both methods. And there you can see that there is exactly that 10% undercall at 1 gram per tonne. So the fire assay really does matter, and the resource geologists have known that for forever. But in broad terms, Aqua Regia is very useful. It depends what you're doing. And I'll also say that's fresh rock. All the samples in the OSNACA database are hypogene 4. The ultrafine fraction that's come in now, it's like the proprietary Newmont bleed technique, but that wasn't available to anybody except Newmont. Now we can. Stream sediment, I would use it all the time. Don't take your stream sediment samples from the active channel. Go to the fine overbank material and send it for ultrafine fraction. Useful for soils where you've got nuggety gold, but I think it's being overused where a cheaper Aqua Regia digest would just as easily do the job. And what I'm really intrigued about is that the refractory elements that are worse than useless by conventional Aqua Regia have some really promising trends on very, very little data. And if people have comparative data sets of ultrafine versus 4 acid, I'd really like to see them. And there's a suggestion that it might work through deeper transported cover in a way that conventional sampling or conventional assaying doesn't. I think that's a case of watch this space. There's so many methods before that have claimed to do the same and have not delivered. It's more expensive, so you really do need to ask, what is this doing for me that standard Aqua Regia don't? Don't use it for rocks. And it's giving us the mineralisation signature and strength. Let's wait and see how effective it is for lithogeochemistry. Now, if we think about gold at various sizes, what I'm trying to get is that nuggety gold is the elephant and the clay fraction gold is the feather or the fly, whatever it is. Now on my computer screen, I could stop that. So just ignore the elephant and the ant. And why that works is if you consider the elephant's body versus its cross-sectional area, there's a stack of ants 100 or 1,000 ants high for every ant-sized cross-sectional area. So that's why the elephant falls off the building so much faster than the ant. And that's why down at the clay fraction size, gold is no longer a heavy mineral. It floats around just like clay. And this is the data that I do have. It was the silliest thing. They did ultra-fine fraction sampling of fresh RC chips. Only 12, unfortunately. I wish they'd done hundreds. And to me, that is extraordinary by an Aqua digest that you're getting sensible comparisons. So the red line is the data and the black line is one-to-one. So obviously you're going to need to scale things, but for working at element associations, you don't need to scale things. It's just the proportions that matter. And the extreme example, wherever it is, tantalum, I don't think the black line's even on the graph. Yeah. Those tantalum values are less than 1/100th of the four acid values, yet they're still, look to me like they're probably reliably scalable, and that's what conventional aqua are definitely not. So let's see, and if anybody can help me out with that, I'd be all ears. Some more elements. This time the Pathfinder, which is what ultrafine should be delivering. That's what it promises. Laboratory checks. I'm going to have a fight out in the corridor with Dale about this. In my opinion, choose the best lab and don't bother. They do far more checks than you ever can, and their reputation depends on getting them right. They're not going to fudge the figures. That practice, in my mind, comes back to 20 plus years ago when the labs, none of them were reliable. But I think the good labs now, for exploration, where we're not so worried about accuracy, I'd leave it to them. Once you get to resource work, there is no choice. If you want to do a JORC compliant resource, you have to have those QA/QC checks. I'm sure there's going to be some disagreement about that, but that's the way I feel about maximising the value of fit for purpose data. We still want to do data checking. They can make mistakes, but the sort of mistakes we're looking for in exploration are howlers, not a 5% error. So we get things like mixed units. Now that's probably in your database, not from the lab. We have for silver there, we've got not a problem, it's just we need to be aware of what's below detection and what proportion of our data are affected. We've got different detection limits for the arsenic that have been given as half the detection limit and stored in the database that way. That's data corruption if you are not preserving the below detection values, so minus 2 ppm, for example. An upper limit of detection, like ICP, OES, or MS, never, ever, ever, ever accept overrange data. Pay and get the real values. The data at the upper end of your distribution are the most interesting. They're the ones that tell you the most. So that's showing there on that probability plot for iron. When it levels out like that, it's really bad news. Here we've got mixed assay methods. So we've got niobium, and you can see that every second drill trace in the middle there is really low. If I used a different color ramp, there would be just as much variation. absolute rubbish. We've got niobium done by 4-acid and niobium done by aqua regia. Here, we just need to know our data. The lab haven't done anything wrong. We've just got mixed assay methods. But then we do get lab errors where we have different batches giving different responses, and we need to get to the bottom of it. And here again from Scott Halley, if you get every second sample screening and then the next one nothing, it's very likely that they've been using 2 mills and you've got an issue with one of them. Repeating the reprecipitation, where we want to do the 2 methods for the same sample, you know, when we'll build that database over time. And this is what reprecipitation looks like. I've put silver on the y-axis. If your data go up like that and then just flatline, you've got a reprecipitation problem. That's what it looks like. And if you look at the probability plots, that's what it looked like. If you've got a pathfinder element, so something rare like silver, it should keep climbing and climbing and climbing to ever higher values when you log the y-axis. When it flatlines like that, or almost flatlines, you've very likely got a reprecipitation issue. Or here, just correlation. We've got 3 samples in the top right-hand corner where we're getting copper correlating with silver and most of the pathfinder elements. So I've given a score out of 3 for those red dots. But at low copper, we've got these really high silver values, but they're not anomalous for any of the other pathfinder elements. I call shenanigans on those silver values. So there we see it in histogram form. It's only elevated for silver. Sorry, probability plot form. So some musts for database. I mean, Dale, I think we'll be in furious agreement out in the corridor on these ones. I hope so. 1 column per element. I can't stand it when I get MgO weight percent, and then other samples in Mg weight percent, and then samples in ppm magnesium. Can't do that, please. Doesn't import into biogas and is a pain for all sorts of other things. Your database output must be 1 column per element. You must preserve those values that are below detection as -X and record the assay method in the database, or at least that comes from in your database output. Or like me, if you're just using Excel spreadsheets to store your data. Yeah, well, this comes from the knowledge of what the different assay methods are appropriate for. If you see aqua regia and 4-acid, in my book, you're absolutely fine to use the pathfinder element suite, your metals, but you can't use your immobile elements in refractory minerals. So compare some, but not others. PXRF is the situation where you are responsible for your QA/QC, because you're the only one in the data acquisition or data capture process. So Dale was saying this too, you must calibrate the instrument properly, and part of that is taking the same sample and getting lab assays and checking not only that you've got good precision, which is a nice correlation, but what is the correction factor that you need to use to get comparable absolute values. You must not accept over range, ever. Does that mean 5 minutes or? Oh, geez, no, it's fine. Yeah, don't replace with half the limit of detection. Yeah. So, have we covered everything? We can't possibly. Donna reviewed my presentation. I don't think she needed to review anybody else's, but she gave me a hard time. But I learned something. 3-acid digest, well, I didn't even tell you about that. Same as 4-acid, but not with HF. And that was determined to be the best option on a mystery project. It's not as useful as the 4-acid to get the alteration and the lithogeochemical data that we get from the more all-rounder method of 4-acid. But what it does do is it leaves alone the sulfide, very fine sulfide that's bound in quartz that they're not going to recover. So as far as the metallurgists are concerned, they want 3-acid values that tell them more accurately the copper that they're actually going to get. And that's the theme of this whole presentation, is horses for courses. There is no silver bullet as far as assay methods go. And I think all of you should take that table and find out where the mistakes are and then learn it. Because that's what we are as geologists. We have a degree in geology, not geochemistry, but we need to be able to, or it's very helpful if we know ourselves what the labs can and can't do. An important thing I forgot to put in there is go and visit the lab, get to know the geochemist so that you know what the options are. He knows or she knows far better than I do what your the really intricate options you have are. This is just like a broad sweeping overview, and it's all I know after 30 years, but you don't need to know that much to be dangerous. So get that best option or options at the best lab. The cost saving on inferior methods or inferior labs will always cost more in the long run. Worst case scenario, it can cost you a discovery. Okay. Thank you.